So next is our hybridization. Hybridization. Now, in hybridization, we have to first know its definition that hybridization is the mixing of orbitals having nearly same energy to produce hybrid orbital. Okay, we have those who have the equal energy. So let's write that it is the mixing of orbitals having nearly same energy, okay, to produce hybrid orbitals of nearly or equal energy. Now there are some characteristics of hybridization. First one is number of hybrid orbital obtained equal to number of hybrid orbitals combined. So what does it mean? Let us assume there is a orbital called sp and there is a orbital called sp2. Okay, so they said the number of hybrid orbitals obtained is equal to number of hybrid orbitals combined. Okay, number of orbitals combined. So what does that mean? I'm going to explain that. That's why I written it first. So here you can see S and P orbital has combined. So two number of orbitals here combined here. So two hybrid orbitals will be formed. And here one and two, one is orbital and two p orbital combined. So three is total number of orbitals combined. So three sp2 or orbitals will be formed. So first characteristic is that. Second characteristic is the unhybridized p orbital can only form pi bond. Okay. So unhybridized p orbital can only form pi bond and sigma bond so formed by hybrid orbitals. Okay. Now third will be all hybrid orbitals are of equal energy and the shape of the molecules will be decided by the orientation of the hybrid orbitals. So that means here this sp and this sp will be of the equal energy. So here also the sp2 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 these three will be also of equal energy. So all the hybrid orbitals have equal energy. Now let us see there are how many types of hybridized orbitals. So there are 6 types of hybridized orbital. First is our sp, then our sp2. So you will see that the p orbital will increase in number here, sp3, then 3 orbitals of p is done, so the next orbital will be naturally d, so sp3d. So d orbital now increase in number, so sp3d2, and last one is our sp3d3. So we are gonna elaborately know how the orbitals and what are their characteristics. So let us discuss the sp orbital. So sp orbital, let us discuss a standard molecule which supports this hybridization, that is our BCl2 or the AX2 form molecule. So now you will ask me that how we knew that this BCl2 will have sp hybridization. That I will explain in the VSCPR theory. Okay, there we are gonna know a particular type of formula that gives our, that is only sole purpose is to give the hybridization and all that, how the shape will be and all thing. So you have to first know that this hybridization is first done for molecules, not this hybridization came first then the molecules came. It is not like that. For particular molecules particular hybridization is practically derived. So to know it theoretically we have to know the VSCPR theory. So we're going to discuss this later. First let us discuss about the bond, how it is formed here in the hybridization. So first let us write the electronic configuration. So it is 1s to 2s2. Okay, as it is 4 atomic number. So here you can see that this outer most orbital has 2 electrons here. So if it is gonna form a extra p orbital, so how it gonna look like? Okay, let us suppose this it has a 2p orbital, but it is empty, right? 2p is 0, but it has to have to form a orbital that is a sp orbital. So here what happens that 1s2, 2s1, 2p1, like this formation happens. Okay, so one molecule is shared here, electron. So these two get merged and form AsP orbital. That's how it is formed. Okay, so how is this molecule gonna look like? So it will be looking like this. Okay, so here you can see it will have a 180-degree angle, bond angle. Okay, and it's how is its shape? If you see its shape, that is linear shape. So sp orbitals have 180-degree bond angle. And what is its geometry? That is linear. These two are the most important points here. You have to remember. Okay. So now let us see the sp2 orbital. So for sp2 orbital, we're gonna and take another standard molecule to explain it. That will be our BCl3. Okay. Now let us write the electronic configuration of B. That is 1s2, 2s2, 2p1. So you can see like this. They have the formation. So this S and this 2p orbitals will take part in this. So what will be their sp2 orbital will look like? So we know that in characteristics that there are 3 orbitals taking part, so 3 sp2 orbitals will be formed here. So and these 3 electrons will get divided in them like this. So it is very simple, you can see. So what will the molecule look like? That's where we're gonna draw here. Okay, it will be looking like this. And here comes another pure vital of Cl, another pure vital of Cl, another pure vital of Cl. So here it is forming a bond. So it is a sp2, it is also a sp2, it is also a sp2. What is the angle formed between two bonds? That is our 120-degree angle. And this whole structure, you can see that it forms a planar structure. So what is this planar structure is called? It is called trigonal planar. Okay, trigonal planar. So what will be the bond angle of sp2 orbital? That is 120-degree, and geometry will be trigonal planar. So now let us discuss the sp3 orbital. sp3 orbital. So the standard molecule for this will be CH4. Okay, so here we are gonna write again the electronic configuration, that is 1s2, 2s2, 2p2. Now, like this previous, we are gonna draw first this. Okay, now it is 1s 3p, so 4 in total. So also sp3 orbitals will form in number 4. So they also have 4 electrons here, right? So they will be divided equally like this, right? So what will be the shape? Shapes are the most interesting things we will learn in chemistry. Okay, so here you can see it is H. So S orbital of H, S orbital of H, S orbital of H. So this is sp3, this is sp3, this is sp3, this is sp3. So what is the angle between these two? So it will be 109.28 degree. Now you can ask me that how is 109.28 degree bond angle is derived. So it is derived practically from laboratory experiment. So just remember it. There is no explanation for it. Okay. So what is the shape that is formed here? Okay. So the shape will be our tetrahedral. Remember it very carefully. Tetrahedral. So bond angle is 109.28 and geometry is tetrahedral for sp3 orbital. So sp3 orbital is also done. Now comes one of the most important orbitals in hybridization. Okay, because many questions came from this. Now we have a rule to understand in this thing later. So from this orbital, you can see that d orbital is including. So they ask you that they will give you 3 molecules or 4 molecules, then ask you in which of these molecules the in the hybridization first the d orbital is included. So you just have to know that in these molecules which have the sp3 hybridization, that will have the first include of d orbital. Okay, so here PCl5 is a standard molecule for this sp3 hybridization. So let us draw the uh, electronic configuration first, that is 1s2 2s2 2p6 3s2 3p3. Okay, so we are doing the same thing we have did in the previous. So you can see 1s 3p 1d, that means 5 orbitals are taking part, so that means 5 sp3d orbital will be found. sp3d sp3d, it is also sp3d, it is also sp3d. So it will be divided like this. Okay, electrons. So for know the shape, where let us see the structure for PCl5, that will be like this. It is also derived from a laboratory experiment, so just remember it. We just have to, if we attach this like imaginary lines, so you can see a particular plane here. Okay, now just see how the shape is derived or the geometry is derived. So you can see that upper this platform there is a pyramidal structure is formed, and also in beneath there is a pyramid structure is formed. So two pyramidal structure, this and they're trigonal in form. So this structure is called trigonal bipyramidal. Okay, trigonal bipyramidal. Now from this we can see that 90-degree angles are 6 in number, 120-degree angles are 3 in number, and 180-degree angles are 1 in number. So you can see here is a 180-degree angle. So 90-degree 1 2 3 4 5 and 6. So and also you can see the 120-degree angles here also. So just remember this, because in the exam you can just draw and then derive and then count. Okay, just remember these numbers. So here a special rule that is called our Benz rule. Okay, so what is the Benz rule called? So it says that more electronegative electronegative atom goes to the axial plane, goes to axial plane. That means we are just drawing it casually because it has all Cl molecules, right? But what if it has this thing PCl3F2? So what we're gonna do then? We're gonna write its structure. So according to Benz rule, more electronegative atom will go to the axial plane. That means fluorine is more electronegative than our Cl. So obviously fluorine will go to the axial plane. Okay. and rest of the CLs are added here. So it is a question of NEET. Okay, so they will give you two structures in one, two or three structures. One, the F, two F will not be in the axial plane, or one of the F will be axial, one of the CL will be axial. So they will ask which is the correct structure. So that structure will be correct, but two F molecules will be placed axially, because in according to Benz rule, more electronegative atom goes to the axial plane. Now this PCl5 has one form in gas, that is PCl5, but it has two forms when it is solid. That is, it breaks in two types of molecules. That is, one is cationic part, one is our anionic part. So here PCl4 have the SP3 hybridization, and here this have SP3D2 hybridization. Okay, so this is also asked. So here our SP3D is done. Now let's see SP3D2 hybridization. So in SP3D2 hybridization, the standard molecule will be SF6. Okay. So let us first write its electronic configuration like we are writing in the previous ones. 1s2, 2s2, 2p6, 3s2, 3p4. So here it will be like this. So we know 1 is 3p 2d, that means 6 sp3 orbitals will be formed. So I'm gonna write like this: 1 2 3 4 5 6 sp3d2 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 sp3d2. And the electrons, they will be divided equally because the orbitals have the same energy like this. Okay, so let us see its shape then. Now it has a very important shape that because of its shape it forms the steric hindrance. Okay, so the molecules becomes very unreactive because of its steric hindrance property. Okay, so let us see that structure. So here is 1f, here is 1f, here is 1f, here is 1f. So just join them like this. So in the previous case, we have seen that the triangular or trigonal bipyramidal shape is forming, but you can see here is a square platform is formed, right? Not triangle. Square platform is formed there. Okay, you can see it. So just let us decide on this color, and if we just march it with imaginary lines, you can see that here is also the pyramid is formed, but it has square base. So what is it will be called? It will be called square bipyramidal or octahedral bipyramidal. Okay. Now for the bond angles, it has 180-degree angles in number 3 and 90-degree angles in number 12. So just remember this, okay? Because you, as I said in the previous class, you can just derive in the exam hall that 1, 2, 3, 4, and it will get very confusing. So just remember this, okay? So here is our SP3D2 is done, and the last hybridization is our SP3D3. Okay, so its standard molecule is IF7. So I'm just going for the structure, as I have already explained how the hybridization is going or forming in the previous cases. Okay, so just join them like this. So you will see after joining them with a particular imaginary line, the base is kind of looking but pentagon, right? This base is looking like pentagon. So if we join them now into axial fluorines, so you can again see a pyramidal structure is gonna form. So what is the structure will be called then? You have guessed right. It will be called pentagonal bipyramidal. So for the bond angles, it has 72-degree angles in number 5, 92-degree angles in number 2, and 180-degree angles in number 1. Okay. So, and here is also a remarkable thing, that is dxy, dyz, and dzx. These three orbitals are taking part in the sp3d3 hybridization forming. Okay, so here is our hybridization is done.